Well, on this video, I'm going to show you how we do an harmonic analysis of a single degree of freedom, a spring mass with damping. By harmonic analysis, I mean that we are going to apply force with some amplitude and with some frequency, get the response, and then increase. This force has a frequency and then an harmonic in a harmonic fashion. Then we are going to go for the next frequency, get the response, go to the next, and so on until we get a full spectrum of frequency in a range that we are going to define. And for each frequency, we are going to capture the response of the system, or meaning the displacement of the mass. I already made this model in Abaqus, and I'm going just to show today how I created the model with the various features. So the first thing is we go in parts, and then we created a mass point. This mass point, it's here, okay, represented by this rigid point here. In previous videos, I showed you already how to build this spring mass system. The mass in engineering features is set to 1 kilo because I'm using SI units. Okay, so these four parts we are done. So parts in the menu here is done. Property we don't need. Assembly, we go in assembly, and then this means that I will go to this menu here, and then I assemble the instance with mass -1. Plus, I also created on the tools here a reference point which is distant from the point connected to the mass, and in between them I'm going to set the spring. The spring on the assembly menu, I go here in engineering features, okay, and spring dash pot, I go here. So the stiffness I set relatively high, a dash pot coefficient 0.7, that means the ratio between force and velocity. We can set, let's say, set to 1. Okay. And then with the assembly, we are also done. So then we did part assembly. Now we go to step. On the step menu, we have this manager here, and then there is the initial step created by Abaqus. And I created a step 1 using steady state dynamics direct, okay, with nonlinear geometry off, but we can put it on. Oh, no, it seems it's not possible for some reason. Oh yeah, because it's harmonic analysis and is within the range of linearity, because it's assumed that the various modes can be added. So then we, just to see what we did here, we add it, and then on this steady state dynamics direct method, I have to put the lower frequency that I have interest to start the sweeping, the upper frequency, and the number of points in between. So I put 100 points, lower and upper frequency as 10 and 20 rods per second. That's okay then. So then I can close this step here. Interaction, we don't have any. Load, we have the force. Let's see what we have. We have load 1 created in step 1. And then we can just to see what has been done here. We put a concentrated force on direction Y, not a concentrated, sorry, an amplitude of our force is 100 newtons. The amplitude is instantaneous, and this is in direction Y, where the motion will occur. So then we can cancel here, dismiss here. So, and the boundary conditions, of course, we need to propagate the boundary conditions between step 1, initial, and step 1. related to this node here. This node needs to be fixed. Okay, so in between this node and the mass, we have the spring. So if I go to edit here, I'm going to see that's encastre. So no displacement, no rotation on that point there. Okay. So load we did, mesh we don't need, and then we can go to job. Okay. And then I created already the job. I run already the case, and then successfully it took less than 1 minute here, and then I can go and check the results. Okay, on the results, then I can see the motion a long time. Okay, uh, there will be then, because I did on purpose when I set the range of natural frequency, this range between, it was between 10 and 20, encompasses the natural frequency of the system. One of the harmonics is within the natural frequency of this mass spring model, and therefore the amplitude is going to grow a lot. We can here put swing, and that's going to give more realistic values, realistic behavior here. We can close a little bit, make it a little bit smaller. Um, the other thing, we can go in view and then go ODB display options, entity, and then show mass inert element with some certain size, apply, and then we see the mass there. Okay. And as for the charts itself, I can create the chart, the XY data, okay, and I can plot this chart as it is here, the displacement, the various frequency between 10 and 20, and the relative displacement here, and then we are going to see that it grows close to the natural frequency. Remember that we have added damping, otherwise this would be going to infinite, and this when the frequency starts carry on growing, and then there is a phase shift here, and then there is the response down here until 20. Of course, if there were 2 or 3 degrees or 4 degrees of freedom, I could enlarge the sweeping frequency here and get the different natural frequency, and then also different modes of vibration. So with this, then we believe that you are capable now to do your own model with 1 or 2 degrees of freedom, and later then this can be evolved to analyze structures which are many degrees of freedom, like beams or plates and so on. So thank you for watching us.